Hello, my name is Steve Bowler, and in this video we're going to be taking a look at Border Gateway Protocol, otherwise known as BGP. We're going to go over BGP communities, the BGP Weight Attribute, BGP Multi-Exit Discriminator, external BGP Multihop, and also BGP Update Source Loopback, and how to implement these within BGP. So what we have is a simple network diagram. We have Autonomous System 100 and we have Autonomous System 200, which are the ISP R1 and ISP R2. Those two routers are in AS200. We have two connections from the customer router to the ISP. We have a T1 and a T3 line. We have 4 loopbacks on the customer router to simulate our back-end customer networks, and on our ISP we have RIP version 2 running as our interior gateway protocol, our IGP. So under the customer router, we're going to go under BGP configuration mode. So we're going to go router BGP 100, and we are going to peer with ISP 1R1. Again, this is going to be an external BGP link. We're going to put in the neighbor command of 130.0.1.2 with the remote AS of 200. And then we're going to also specify the connection on the customer side. We'll do the neighbor command for the 1.2 as well, and we'll do the update source loopback 5. So we're going to be using the loopback 5 interface for the BGP updates to come in on. Instead of the physical interface, we're going to be using a logical interface, our loopback interface. And we do that with the update source command. So we're going to use update source loopback 5. So BGP should be sending and receiving updates on this interface, or using this as the source for the BGP traffic. And then also on the customer router, we're going to specify the EBGP Multihop command, and we're going to set this to 2. So all this command is doing is saying, in the normal operation of BGP, external BGP, you would peer directly to the interface IP address, the physical interface IP address. So with the EBGP Multihop 2, this is changing the TTL value of 2, which allows the hop, instead of being directly connected or having one single hop from one interface to another, EBGP Multihop 2 will allow us to bypass this default external BGP configuration. So this goes along with the loopback update source loopback command. That way the router will be able to go to the loopback for the updates, for the BGP updates. So that's what EBGP Multihop 2 allows us to do. Without that command, our BGP neighbor relationship would not form correctly. So this will allow us to peer using our loopbacks. So on ISP R1, we'll go ahead and configure ISP R1 for BGP AS200, and we'll put in the neighbor command 130.0.1.1, which is our customer 1, for remote AS of 100. And the loopback is going to be loopback 1 on ISP R1. So we will configure the neighbor, which is the customer router. We're going to receive these updates to source these from our loopback 1 interface. And the only way this is going to be allowed to happen again is with the EBGP Multihop being set to greater than 1, because the time to live by default is set to 1. With that being said, that TTL will die out and we will not be able to form a BGP neighbor relationship. So that's why we use the EBGP Multihop 2 command. It allows us for that traffic to get to our loopback now. Now, external BGP Multihop is usually implemented when you have two external neighbors which are connected via multiple links or multiple sessions like ATM, frame relay. So if one of those circuits goes down, the connection needs to be alt routed. You have the EBGP Multihop set up to 2 or more so that your network will not be affected by a network outage on one link. And the last thing that we are missing in this EBGP configuration type is a static route. So again, this type of external BGP peering is a little different than normal, but you will see this in the real world a lot. So you have to be familiar with doing this. So under global configuration mode, we're going to create an IP route. So we're going to put the network we want to reach, which is the 1 network, which is loopback 1 off of ISP R1, using the host mask, which is the /32, and then we're going to specify the outgoing interface, or the neighbor's interface. So 130.0.1.2. So how are we reaching this network? And that is going to be via ISP1R1. So we have to do this bidirectional. So we're going to go on to ISP1R1 and create the IP route to the customer's loopback 5 interface. So again, how are we going to reach the 5 network with the subnet mask of /32? We're going to reach it via the next hop of 130.0.1.1, which is again our connection to the customer router. And so now let's see what happens. We'll give BGP a second to peer. BGP is a slow protocol, but that is a good thing in some cases. So if I do on the customer side a show IP BGP summary, we can see that we do not have a neighbor relationship yet with ISP1R1. Let's go to ISP1R1 and do a show run. And we're just going to verify and validate that we have the correct configuration set up on both of the routers. Okay, so it looks like the connection has not come up yet, and I can tell you why. We put the wrong neighbor statement. We actually put the wrong neighbor statement in. Instead of neighboring on the customer router, if we go under, we'll blow away these neighbor statements. We'll go under router BGP, we'll do a no neighbor, and then we're going to change instead of, like we were saying earlier, when we peer EBGP to a loopback, we're going to actually putting in the neighbor statements. So on the customer router, we're going to peer with the neighbor command to the loopback. So we're going to do 1.1.1.1 with the remote AS of 200. So also we'll go back under BGP and we will add our neighbor statement of 1.1.1.1 with the update source with the loopback of 5 and neighbor 1.1.1.1 EBGP Multihop 2. So that should be the correct configuration. Again, when you're doing this type of configuration using EBGP Multihop and updating your sources from the loopback, you do not put the physical IP address on the interface to peer with your neighbor. You actually put your loopback that you're peering with the neighbor. So very important to remember in your configuration. Again, instead of the actual physical interface that you're putting your neighbor statements, the IP addresses in, we are peering now to the neighbor. So on R1, ISP1 R1, our neighbor statement is going to look like this: 5.5.5.5 with the remote AS of 100. And then also we're going to point this neighbor to receive updates on loopback 1. And then the last command under the neighbor is 5.5.5.5. And then we're going to specify EBGP Multihop of 2. So as we can see, that's good troubleshooting for you. If you have a EBGP Multihop configuration set up and your neighbor relationship is not coming up, make sure that your neighbor statements are peering to the loopback that you're trying to update your source traffic from, or receive updates on the loopback, and also make sure that you have your static routes in pointing towards the loopback of your neighbor. So good troubleshooting tips for you. And now we can see that our neighbor relationships are coming up. And on the customer router, I can ping the one network, and on ISP1R1 I can ping the loopback 5 off of the customer router. So if we do a show IP BGP summary, we can see now that we have been up for about half a minute with ISP1R1. So this is a successful external BGP multi-hop configuration. So the next step is to configure the other side that is pointing towards from the customer router to ISP1R2. So again, under the customer router, we're going to go into router BGP 100. We're going to do the neighbor statement. Actually, let's configure R2. We'll go under BGP Autonomous System 200. Do a show IP interface brief to make sure we have the IP address and the loopback. Let's go ahead and create the loopback 2 interface. Get with the IP address of 2.2.2.2 with a /32 subnet mask. Now if I go and do a router BGP 200, we will do a neighbor, which is going to be 5.5.5.5, which is the customer loopback 5 interface, and we will specify the EBGP connection with the remote AS of 100. We will also specify to receive updates from our source of loopback 2, which is the loopback interface we just created, and then we will also put in the last command, which is neighbor 5.5.5.5 with the EBGP Multihop 2 command, which is setting our time to live instead of the default value of 1 to 2 now. And the last step from global configuration, we're going to add our IP route, our static route, to reach customer 1 or the customer's Loopback 5 IP address. So IP route 5.5.5.5/32 subnet mask, and then the exit interface or the next hop, valid next hop to reach this, which is 130.0.2.1, which is the customer's physical interface pointed towards ISP1R2. So now let's get the configuration set up on the customer side. We're going to specify our neighbor. Again, we're using the loopback interfaces and not the physical IP addresses on the EBGP connection. Remember, we tried to do this earlier in our configuration and it failed. So we do not want to do that. Just wanted to show you that just in case you were to see that ever. Good troubleshooting. So we'll do neighbor 2222. Update source is going to be Loopback 5. We'll also do the EBGP Multihop 2. And then the first neighbor statement we put in the remote AS of ISP1R2, which is in AS200. So our last statement is we're going to put in our static route to how are we going to reach the Loopback 2 on ISP1R2. So we'll put in the IP address and then subnet mask, or the network and then subnet, and then we're going to put in the valid next hop IP address, which is 130.0.2.2. It's very critical that you remember the static routes when doing external BGP multi-hop configuration, as well as peering with the neighbor IP address of their loopback and not the physical interface or the physical IP address of the interface. So now if I do a show IP BGP summary on ISP1R2, we can see our BGP neighbor relationship has come up, and now we have both of our connections from the customer router to ISP1R1 and ISP1R2. So let's go ahead and try to ping the two networks from the customer router, and we are successful. And then we'll do the same thing from ISP1R2. We will ping the Loopback 5 IP off the customer router. Okay, so now that we have full BGP reachability, I'm sorry, we don't have full IP reachability. What we're going to do is we're going to configure an IBGP connection between ISP1R1 and ISP1R2. So again, this is an internal BGP connection because both routers are in the same BGP autonomous system, which is 200. So in this example, we're going to do neighbor 1.1.1.1, update source Loopback 2. I'm sorry, let's do the remote AS command first, remote AS 200. And then we will do, after the remote AS command, we'll do update source and then Loopback 2. Okay, so now let's go to ISP1R1, and we'll go under BGP configuration mode for AS200. We'll do the command neighbor 2.2.2.2. We'll do the remote AS200, and then we are going to do the option of update source Loopback 1. So again, Both of these routers are using their loopback interfaces as the source of the BGP traffic. What we want to do is advertise the loopback interface into BGP. So network 1.0.0.0. Also, we'll do this on ISP1R2. We'll do network 2.2.2.2 mask/32. So again, that's very important. Let's take that command out, the no network 1.0.0.0. Let's do network 1.1.1.1 with the mask of /32. And what we are seeing thus far is we are not seeing a BGP neighbor relationship between these two routers. So let's take a look. If I do a show IP route on ISP1R1, we do not know how to get to ISP1R2's loopback interface because it is not in our routing table. If we do a show IP BGP summary, we can see that we never have had a appearing with ISP1R2. So if I do a show IP route on ISP1R2, we have the same problem. We do not have a route to the loopback 1 interface on ISP1R1. Again, this is an IBGP connection between both of the routers. They are peered correctly with the correct neighbor statements. However, there is no IP reachability in the routing tables on both of the routers to the other side. So we don't have, again, we don't have reachability to the loopbacks. So we're peering on the loopbacks, but we don't have reachability to the loopbacks, as we can see in the routing table of both of the routers. So let's just go into RIP on both of the routers, since we're running that as our IGP, our interior gateway protocol, and we're going to advertise those networks into RIP, and then we should see reachability. So we'll do the network statement under RIP for the 1 network to advertise our loopback 1 interface on ISP1R1. So if I do a show IP route on R2, we can see that RIP network now. And then we'll go and configure ISP1R2 under RIP. We will advertise the network of 2.0.0.0. And now we can see our BGP neighbor relationship come up. So our neighbor adjacency has come up. Our IBGP connection between ISP1R1 and ISP1R2. So now if I do a show IP BGP summary, we can see that we have peered from ISP1R2. We have an adjacency now to neighbor to ISP1R1. Same thing on ISP1R1. If I do a show IP BGP summary, we are seeing ISP1R2 as a neighbor now for over 30 seconds. So that is how you peer using the update source loopback and EBGP Multihop via IBGP. So the next thing we're going to do is go under the customer router under BGP 100, and we're going to advertise our local networks into BGP. So we'll do that with the network 140.0.0.0, and then we'll supply the correct mask, which is /24, for the 0 network, the 1 network, the 2 network, and also the 3 network. So now if I go to router 2, ISP1R2, and do a show IPBGP, we can see that we are only seeing one 140 network. Just took a minute to propagate. Now we can see all the networks. So give BGP some time. Again, like I was saying earlier, it's a slow protocol to converge. So what we can see is this I next to these routes mean that they are inaccessible. If I do a show IPBGP 140.0.0.0, my external route is the best. And that is because external is going to be preferred over internal BGP. So if I go under router BGP 200, the next thing I have to do is my IBGP neighbor relationship to ISP1R1, we have to set the next hop self command. So let's go ahead and do that on ISP1R1, because by default to an IBGP peer the next hop is not changed. In external BGP it is changed. For internal BGP the next hop is not changed. So we need to manually do that under BGP configuration with the neighbor statement. So we're going to do the neighbor statement to ISP1R2, and we will set the next hop self. So now if I look at the routing table, what we can see now is that we have a valid next hop for these routes. Instead of the 5, it's showing 1.1.1. I'm sorry, 1.1.1.1. So right now on ISP1R2, the best path to the customer routes are through its external BGP connection, like we saw when we did the show IPBGP on the prefix. We should also see that in ISP1R1 when we do show IPBGP as well. We see that also with the caret next to the network. This is what's added to the IP routing table. This is the BGP topology table. Again, with the caret next to it, that means it's going to be added to our local routing table on the router as the best path to the destination. So far what we've gone over external BGP Multihop. We also went over BGP update source loopback. We looked at troubleshooting that. The next thing we're going to look at is the BGP Weight Attribute, and we're going to show you how to configure that and why and when you would use the Weight Attribute within BGP. So when we use the Weight Attribute, this is a good example. We have a customer network. We have one edge router that's running BGP, and we want to use the weight attribute to influence our exit path from our local AS, which is AS 100, out to the rest of the world, or to the ISP routers. Again, weight is a Cisco proprietary BGP attribute that is only spoken to the local on the local router. The weight attribute does not leave the local router, whereas the BGP local preference attribute does. The weight attribute is specifically local to the router, which means it is only important on the local router. The weight attribute does not get passed along to other IBGP neighbors within the AS. So if I try to ping 1.1.1.1 from customer router, you can see that we are successful. Also, the 2 network, we have reachability. We can see that we are reaching the 2.2.2.2 off of ISP1R2. The next hop is the direct connection to ISP1R2. So if I do a trace from the customer router, if I trace, actually say that connection to R2 is a T1 link, and obviously the T3 line is, we want to prefer that as our outbound interface, because our T1 is 1.5 meg, where the T3 is going to give us 45 meg connection out to the ISP. We can use the BGP weight attribute to influence our outbound BGP or our outbound traffic from our local AS out to the service provider, our ISP 1. So if I do a show IP route, we are seeing the 2 network with the next hop of a 130.0.2.2, which is the external connection to ISP1R2. We have 2 paths to get to the 2 network. Right now it is preferring the connection through ISP1R2. So we can look at a way to change this default behavior by using the weight attribute. We will go under BGP 100 and we'll do the command neighbor. We'll do the command neighbor 1.1.1.1, which is the connection to ISP1R1, and we will specify after that the weight attribute. Now for weight, the higher weight is more preferred. So what we will do, all of these weights have no value, so what we're going to do is change the weight to 200. And then hit enter. So we'll go ahead and do a clear IP BGP. We'll do a soft clear on the neighbor. Again, this is not going to bring the connection down, it's just going to do a soft clear. So now when we do a show IP BGP, we can see that the weight has changed, and we can see that before we were seeing the best path through to the 2 network, it was via router 2. Now we are seeing the best path to the 2 network with the next hop of ISP1R1 with the weight of 200. So now if we do a trace to our destination network, which is the 2 network, well, let's see what way the traffic flows. Okay, sorry about that. It looks like what we did was the loopback interface that we were using, I forgot that we had a static route pointed towards those loopbacks. Even if I did change the weight, this is a good example of showing you this. Even though I did change the weight value on those routes, we were still going through the T1 connection, and that is because we had the static route in our routing table pointing towards those connections. So we all know those static routes have a lower administrative distance than external BGP, which is 20. So those static routes were being preferred. So what we did for the example in this lab was we created another loopback, which is loopback 20. And if we do a show IP BGP on the customer router, we are seeing the 20 network that we created, which is 20.2.2.2. It is showing the next hop through R1, which is our preferred T3 connection. So again, the reason why that did not work, even though we did a show IP BGP, we saw that it was changed. First, it was preferred through ISP1R2. Then we saw when we created, changed the weight, it was going to ISP1R1. But that was specifically for BGP in the BGP topology table. The static route trumped BGP because it had the lower administrative distance. BGP has an administrative distance, external BGP of 20. The static route had administrative distance of 1. So of course that static route pointed to the loopback 2 on ISP1R2. That's why that won that decision. So we had to go and create a loopback 20 interface off of ISP1R2 and advertise that into BGP. So now when we do the trace, we are seeing it go out the T3 connection to ISP1R1. And then with the next hop of 1.2, which is the connection between ISP1 to ISP1R1 to ISP1R2. So we're going to use MED now, the multi-exit discriminator. This is how the return traffic from the ISP network coming into the customer network. So another thing with MED, it is only carried between the local AS. It does not transit through multiple autonomous systems. The MED attribute is only propagated throughout the local autonomous system, kind of like local preference. But it is only advertised out to that local autonomous system. So in this case, we can set up the MED on the customer router, basically telling the ISP this is the preferred route to get to my internal networks, use this path instead of, use the T3 path instead of the T1 path. So next we're going to be taking a look at the BGP MED attribute. So before we influence MED, we can go to ISP1R2 and do a show IP BGP. We can see the best path from ISP1R2's perspective to these 140 networks, or these customer routes, is via our external BGP connection. That is the more preferred path. So if we do a show IP BGP on one of the customer networks, which is in this case 140.0.1.0, we can see the external BGP connection wins. And we know that because it has the best option next to it. But we know with the diagram that this is the T1 connection. Say we want to advertise our networks on the customer autonomous system to go through R1 inbound. So all traffic coming into the customer AS, we want to prefer this traffic inbound through the T3 connection. So the way we're going to do this is set up an access list on the customer router. We'll just create a standard access list. We can be as specific as we want or as general as we want. In this case, we're going to just use a simple standard access control list of 1, and we're just going to permit any traffic. So all of our routes we're going to permit, and then we're going to create a route map which will be called med out. So we're going to be advertising this med out to our ISP, and then we're going to do the option of permit, and then with the route map we're going to match our IP address 1, which is the access list 1 that we just created, which is permitting all traffic. And then our next option is, once we have the match option under the route map, we're going to do the action that we want to perform with the set command. So we're going to set the metric, in this case the lower med is more preferred in BGP. So what we're going to do is we're going to set the metric, in this case we'll set the metric to 100. Actually, let's go ahead and do 200 for the metric. And then we'll go ahead and we'll exit out of our route map. And then we'll go under BGP configuration for autonomous system 100. And this med, this is how we're going to implement the multi-exit discriminator. This is going to be the connection to ISP1 R2. So we'll do the neighbor statement towards ISP1 R2, which is neighbor 2.2.2.2. Then we will follow it up with the route map statement, and then we'll put in the name of our route map, which is med_out. And then again, inbound or outbound, we're going to be sending this out towards ISP1 R2. So the next thing we're going to do is create another route map. We will also call that, let's go ahead and call this med_win_out, and we are going to permit. In this, we're going to match our ACL1. So we'll do a match IP address 1. So we're going to match ACL1, which is permitting everything, and then we're going to set the metric to 100 inside of this route map. So we are going to configure this, as you might have already guessed. We're going to go under BGP configuration mode, and we're going to specify this for the neighbor relationship to ISP1R1. So we'll do the neighbor 1.1.1.1. And we are going to do the route map command. And then the name of our route map, which is med_win_out. So med_win_out, and then the direction in which we want to send this, which is outbound. So we're sending this out towards our ISP1 routers. So what we should see is the metric for pointing towards router 2 should be 200 for all of our routes, and then the metric for all the routes towards ISP1R1 should be 100. So let's go under ISP1R2 and see if that took. And yes, we can see now that the metric for the 140 networks, we are now receiving the inbound metric of 200 for our external BGP connection. So now it's preferring the IBGP path through ISP1R1 to get to the customer networks, because that is the T3 connection. So let's go under ISP1R1 and take a look and see if that is what we are seeing as well. If I do a show IP BGP on ISP1R1, what we can see on ISP1R1, we can see the best path through the 140 networks is through our directly connected, or through the EBGP connection to the customer network. And from router 2, it has changed as well. It is now preferring the path with the lowest metric, which is via R1, ISP1R1. So if I do a trace to the 140 network, 140.0.1.1, we should see that our inbound path selection has changed. Instead of the external BGP connection, we should be taking our internal BGP connection via R1, because it has the lowest med. So it looks like we got some asterisks here. So what we can do to remedy this is if we go to ISP1R1, let's go under router BGP 200, and we can send our neighbor a default route. So we'll just do neighbor 5555 default originate, and on the customer router, if I do a show IP BGP, or if I do a, we see a default route now being sent via BGP. So let's go back through and see if the trace works correctly now. So again, this is how we can manipulate traffic inbound to our AS using the med attribute on the customer router to prefer our T3 connection instead of our T1 connection. And now we can see that the trace went through, and and now router 2 is preferring the connection through R1 to get to the loopback interfaces off of the customer router. So before we were using the direct connection to the customer router over our direct connection over the T1. So that's how you successfully configure the MED value, the multi-exit discriminator, on the local customer router to direct traffic from the ISP back into your AS. So again, the MED value is only propagated out to your neighboring autonomous system, and that's it. That's where it stops. It doesn't go any farther than the next AS in the path. So the next thing we're going to do is go over a couple of basic things with BGP communities. BGP communities enable you to apply policies to a group of IP prefixes, subnets, or routes. And the community attribute is communicated from one BGP router, speaking router, to another. So what we can do is group routes on our customer router and we can tag them into a community and send this community information out to the ISP BGP autonomous system. So we're going to go over some basic BGP communities. So let's say our routes 2 and 3 we want to create in community 1. We'll do this. We'll go under the customer router. The first thing we're going to do is create an access list. We'll just do a show IP access list just to verify the current ACLs on the router and that we don't overwrite anything. And then we'll do an access list. We'll just name it 23 for the prefixes of the 2 network and the 3 network. And we're going to permit 140.0.2.0 with the wildcard bit of 0.0.0.255. And then we're also going to put in the 3.0. So the next step, we're going to create a route map, and we will call this route map, we're going to call this route map send_com for send community, and then _23 . And then under the route map, we're going to match the ACL that we just created, which is access control list 23. And then once our traffic matches this ACL, we're going to define our action, which is going to be to set the community, and then this is where we can apply our community value. We have a autonomous system and a community number. So we can put in, I'm sorry, not autonomous system, our community number, and then community number in AANN format. So we're going to use 100:23. So the 100 represents our AS, and then 23 is our community number. So let's go under router BGP 100, and we are going to do the, let's go to, we are going to send this to ISP1R1. So we were going to do the command neighbor 1.1.1.1, and then we're going to put in the command send community, and then the next statement we're going to do is, this is going to specify what neighbors we are sending this community attribute to. So we are going to specify ISP1R1 as our neighbor. And then the next step we're going to do is specify our route map that we created. So we're going to do neighbor 1.1.1.1, and then route map that we created, which is the route map of the name of the route map, which is sendcom3, and we're going to apply that outbound. Again, which way are we sending it? Inbound, outbound. In this case, outbound to the ISP router. So the next step, we're going to go under ISP1R1, and if we look at a specific prefix set under community 23, let's take a look. We'll go on ISP1R1, we'll do a show IP BGP, and we will specify one of the networks under that community, which is 140.0.2.0. It has not been propagated yet, so again, whenever you're messing with route maps or access control lists or any type of filtering or route manipulation, best practice is to do a soft clear on the BGP neighbor. So from ISP1R1, we're going to clear our BGP neighbor relationship to the customer router. And now when I do a show IP BGP on the prefix within that community, which is the 2 network, we can see the community tag is now being propagated. So this is not, by default, this is not the correct community value that we applied before. We applied the community under the route map to 100:23. So this community is, this is the old decimal format for the community. To change the format, what we have to do is, to change this, we put in the command IP BGP Community new format command under global configuration mode on ISP1R1. So now we can see the community in the correct format that we created it in. So again, this is under ISP1R1. We changed the format to IP BGP Community new format. So this is showing us what autonomous system this is from, and the second part is the community number. So let's go to ISP1R2, console into it, and if I do a show IP BGP on one of the prefixes inside of that community, which is the 2 network, what we can see is that we are not seeing the community value being propagated from ISP1R1 to ISP1R2. So we aren't receiving the community again from ISP1R1. So what I did, I paused the video for a second. What I did was I went under ISP1R1. I had to go under BGP configuration mode, specify the neighbor, which is our ISP1R2, and do neighbor 2.2.2.2 and then send community. So now if I go to ISP1R2 and do a show IP BGP on the prefix, say on the 3 network, we can now see the valid community string. So again, this is the old community format. So when you're seeing it not in the new community format, we can change this by going under global configuration mode, do an IP BGP community new format, and if I go back and do a show IP BGP on that prefix, we can see the correct format in which we configured this for originally on our customer router. Which is 100:23. So there's a lot of things you can do with BGP communities. One of the real powerful tools, say on the customer router, if I only wanted my ISP to see these routes, the 2 network and the 3 network, what I can do is go back into this route map that I created, which is send com23, again we're going to match IP address, we're going to match our ACL 23, and then we're going to use the set community. We can see we have many options. One of them is the no export, which means do not export to next autonomous system. So if I do set community no export now on these routes, which is the 2 network and the 3 network, again, we just want to look at the route map just to make sure we have the correct logic in there. If I do a clear IP BGP on ISP1R1, do a soft clear on the neighbor, and let's go into ISP1R1. We do a show IP BGP on the prefix, which is on one of the community prefixes. Now, right after the community string, we have the no export. So what this is going to do, it's going to advertise this community only to the ISP autonomous system, which is at AS200. If we had another router behind the ISP network, say we created a 3rd router, say to another ISP, which is in AS300, if we had an EBGP connection from 200 to 300, and we went on to the router on AS300, we would not see this community string anymore, because we have configured this community with the no export, which means that the routers in AS200 will not advertise this community outside of AS200. So that's the power of the no export feature within BGP communities. if I am receiving incoming community updates, I can also manipulate those as well in my network. So I can override the community statements or attributes that the customer router is sending to us regarding these two networks. So the way we can do this is if we go under ISP1R1, go under Global Configuration Mode, create an access list, a standard ACL called, name it 23, and we're going to match these two networks, so 140.0.2.0/24 wildcard. Also do this for the 3 network. The next step is to create the route map. We'll just call it deny _com, and then permit. We're going to match the ACL we created, which is 23, and then we're going to do the action, which is set community none. So before I do this, if I go to ISP1R2, let's go to ISP1R2. If I do a show IP BGP on the 3 network, we can see we are receiving the community of 100:23 no export from my peer ISP1R1. So what we're going to do on ISP1R1 is we're going to manipulate the community values that we are receiving from the customer. We are going to set the community to none. So this is going to override the community statement that the customer has sent to us regarding this network, these two prefixes, which are the 2 and the 3 networks. So the next step is to go under router BGP 200 on ISP1R1, and we're going to send this route map that we just created to ISP1R2. We do that with the neighbor statement of 2.2.2.2, follow it up with the route map, and then the route map that we just created, which is deny_com, and then the direction, which is outbound towards. So if we look at the traffic flow, customer is sending us the community string to ISP1R1. ISP1R1 is taking this community attribute and overriding it. We're manipulating it. We're actually just going to set the community to none. So if I hit enter under ISP1R1 and go into ISP1R2 and let's do a quick clear on the neighbor. We'll do a clear IP BGP .2.2.2.2 soft. And now if I do a show IP BGP 140.0.3.0, now we can see that there is no more community statement or information being propagated from ISP1R1 to ISP1R2 because we just deleted the community that the customer sent us in regards to these two networks. So now if we want to delete that, let's just go into ISP1R1. We will go into BGP 200 and we'll just do a no on the neighbor statement on the route map that we sent to ISP1R2. So if I do a show route map, it's still going to keep the route map, just delete the statement going to the neighbor. So let's do another soft clear within BGP towards ISP1R2. And then if I go to ISP1R2, we can see the community being propagated again, which is 100:23 no export. So the last thing we're going to show you in this video, there was a lot more that you can do with communities. We're just going to give you the basic rundown of communities and their power and how they can be used. If we look at the BGP table, we are not seeing all of the routes going through router 1 at this time. And this is, we're only seeing 2 routes going through R1. And 2 of those routes we're seeing go through router 5. And that is because we created the route map under the customer router. If I do a show route map, remember we had a med route map on there before going out to our neighbor, but you can only have one route map going outbound to your neighbor at a time. So when I applied the community route map that I created, the med route map that I created was taken off. And we can see that if we do a show run pipe to begin BGP, we can see out to my neighbor, which is ISP1R1, we only have the one route map, because you can only send one route map at a time out on a per neighbor basis. So with that said, what I need to do is go back into this route map and fix it so that it has all the information that we set up before. So we'll just create another permit statement. For sequence 20, we'll just set the metric to 100. So if we look at the old route map, that's what we did. We set the route map to, or the metric to 100. What our new route map is doing is it's only matching, if you match this access list 23, then we're going to set the metric to 100 and then add the community. So if we leave it like that, all those other routes that we're sending are not going to be tagged with a metric of 100. So what we need to do is we need to create a second statement under our route map, send community 23, and set the metric to 100 for the rest of those routes. So again, on ISP1R2, we should see the network 0 and 1. We should see the next hop of being ISP1R1 again. So again, we're preferring the T3 inbound from AS200 to AS100. But right now, the T3 connection is not being preferred. Router 2 is just taking the straight shot, the T1 path to the customer router. So once we apply the statement to our route map, we should see our optimal routing back to normal. Our optimal path be the preferred path again. So now if I do a show route map for send community 23, we have two sequences. we have sequence 10, which is matches the ACL 23 and setting the metric of 100 and setting the community. And we also have the sequence 20, which is going to match everything else that doesn't match this first sequence. It's going to permit this and set the metric to 100. So all other traffic will be given a metric of 100. Again, when you're messing with filtering, route maps, prefix lists, it's always good, best practice to do a soft clear within BGP on your neighbor. So let's go back to ISP1R2 and do a show IPBGP, and now we can see the optimal path is being taken again. We can see these routes being with the best path to the customer router via ISP1R1 going over the T3 connection. Again, lower metric is going to beat higher metric value. It's seeing the metric of 200 via the T1 connection. Again, the customer is sending us this metric of 200 over the T1 link, and then the customer is also sending us a metric of 100 over the T3 link, the ISP1R1. In metric, or within the med, the lower med wins. So that is why these routes are now being preferred through ISP1R1. So now if I do a show IPBGP on the 2 network, we are still seeing the metric being advertised as 100, and we also seeing the community value or the community attribute being applied as well. So they are both being set correctly. So all we did was a little route map manipulation and we got it to work. So again, one route map at a time can only be applied to one neighbor outbound. So in this lab we covered BGP update source. We also went through external BGP multihop and why you would use that. We looked at troubleshooting external BGP multihop and the problem you might find doing that. We also configured the BGP Weight Attribute. We also configured the BGP Med Attribute, and we also showed you guys a little about BGP communities and why and when they would be used. So thanks for watching the video, and I hope to see you in the next one.